What about lone pairs? There are molecules that have one or more lone pairs in the central atom. What does that do? When there are lone pairs, we talk about two different kinds of geometries. There's the electron geometry and the molecular geometry. Electron geometry looks at the arrangements of the electron groups, and a lone pair is an electron group. Molecular geometry looks at the arrangement of the atoms. If there aren't any lone pairs, they're exactly the same. The way I think of it is a lone pair is like a single bond to an invisible atom, or a single bond to nothing. The molecular geometry is what you can see. It's the atoms. And the electron geometry is what the electron groups are doing. Let's look at ammonia. Let's look at the Lewis structure for ammonia as well. How many groups around the central atom? 4. There's 3 single bonds and a lone pair. 4 groups arrange themselves in a tetrahedron. So they're going to make this tetrahedron. There's 3 atoms and the lone pair. That's the electron geometry. The molecular geometry is we're only looking at the atoms. This is what the atoms are doing. It's like, okay, this guy's invisible. If he's invisible, if we can't see him anymore, what do we have left? Well, this is called a trigonal pyramid. It's trigonal, but it's not flat. Trigonal planar is flat. It's squashed. This sticks up a little bit. And what do you think the angles are here? From a tetrahedron. The angles are 109.5. So these angles are 109.5 approximately. So think of the lone pair as being invisible. It's there. It's repulsive. It's actually more repulsive than the hydrogen atoms. This is actually going to be a little less than 109.5. But when we talk about the molecular geometry, we don't include what's invisible. Any questions?
Will lone pairs always be invisible?
Yeah. In chemistry land, electron lone pairs are always invisible because they're so small. They're so crazy tiny. So those lone pairs actually are more repulsive than bonding pairs because they're more spread out in space. If we look at a bonding pair of electrons, so here's one nucleus and here's the other nucleus, and the overlap of those orbitals, that is going to give us this constricted shape. The lone pair, on the other hand, is more spread out. So if you've got this guy up here, it's going to push these guys together. This is ideal tetrahedral geometry, but the actual geometry, the angle is only 107 degrees because the lone pair is repulsive. And so it repels these more and squeezes them together a little bit. Let's look at water. Water is just a crazy, crazy substance. So if we just draw the Lewis structure for water, we end up with this. And if you were just looking at that, you might think that water would be linear, right? 2 hydrogens bonded to an oxygen, it'll make a line. But it doesn't. There are 4 electron groups. There's 2 lone pairs and 2 single bonds. 4 groups form a tetrahedron. But now 2 of the corners are lone pairs. Electron geometry is tetrahedral. Molecular geometry, it's like these balloons are invisible. This is what we have left. And that is given the very, very fancy name, bent. Okay? It's just bent. Bent. So here's the ideal geometry, 109.5. We've got 2 lone pairs out here now. They're going to squeeze these hydrogens together even closer than in ammonia. And so the angle for water is 104.5. So in terms of relative repulsion, lone pair is the most repulsive combination. Lone pair bonding pair is next, and the bonding pair is the least repulsive. And so when we look at methane, all we have are bonding pairs repelling each other. So the angles are going to be equal at 109.5. Here we have one lone pair, and it's causing these guys to go together, 107. Here there's two lone pairs, and that squeezes this even more. So what's the difference between these two angles? 109.5 minus 107 is what? 2.5. And what's the difference between 107 and 104.5? 3.5. So, I'm sorry, 2.5. So there's kind of a pattern there. You add a lone pair, the other angle decreases by 2.5 degrees. Let's look at SF4. We need the Lewis structure first. So we've got sulfur, and we've got 4 fluorines. How many electrons do we have here? Sulfur's got 6 valence electrons. We've got 4 fluorines. They each have 7. So we've got 28 plus 6, that's what, 34? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 32, 34, sorry, 32. I counted wrong somewhere, but there's 32 on there. What do I do with the last pair? Put it on the sulfur. Because sulfur is in period 3 of the periodic table, and sulfur can expand its octet. If you just looked at the formula for S4, you might predict that it was tetrahedral, right? Because there's 4 atoms bonded to it. But when we look at the Lewis structure, we see there are 5 groups. 5 groups makes a trigonal bipyramid. A bipyramid, right? Well, then the question is, where is this lone pair going to go? If the lone pair goes in the axial position, it's got a 90-degree interaction with the equatorial ones. If it goes in the equatorial position, it has a 90-degree repulsion with those two, but a 120-degree angle with these guys. So here it's got all 90-degree interactions, and here it only has 2. So this is going to be better. It's going to go over here. So when we make that invisible, we get this funky shape, which, you know, kind of looks like a little stick person holding their arms out. I don't know. But that doesn't help us because that doesn't give us the name seesaw. So let me try to draw it sideways. That's very, very bad. Sorry. So here's the pivot of the seesaw, and here's one seat, and here's the other seat, and they go up and down this way, right? I'll get out some model kits that we can mess around with during lab. But it's called a seesaw. This would be called something else. Actually, I'm not sure what that would be called, but it's not the same as this. And so if you have one lone pair out of 5 groups, it's going to be a seesaw shape. BRF3 has 5 electron groups. There's 2 lone pairs. Good, because I was tired of drawing Lewis structures. So here the bromine has 2 lone pairs and 3 bonds. 5 gives us that trigonal bipyramid, but now we have 2 lone pairs. So lone pairs are going in the axial position because they're more repulsive and they've got more space there. And so then we end up with this, and that has the clever name T-shaped. It's shaped like a T on its side, the way they drew it. All right, shaped like a T. 90-degree angles. 5 groups, 2 lone pairs. There's a table in your book that just summarizes all this stuff. I think I've got it in the slides too. That's nice to refer to, but I think it's really best to look at the number of groups, visualize, okay, how would that many groups get away from each other? And then, are there lone pairs? Let's make those invisible. What do we have left? Xenon difluoride, 5 electron groups again. This time there are 3 lone pairs. The 3 lone pairs are going to take the equatorial position, and we're going to get a linear geometry. So xenon difluoride is linear. And it does that to minimize the repulsion. Bromine pentafluoride. 6 electron groups with one of them being a lone pair. So this is the octahedron, but now one of these is a lone pair, so it's invisible. And what's left? It's a square pyramid. So we have a square at the base coming up to a point. It's a pyramid. These are equivalent. They're all 90-degree angles, so it doesn't matter where the lone pair is. You'll still end up with a square pyramid. Xenon tetrafluoride, again with the 6 groups, but now 2 lone pairs. The lone pairs will be opposite from each other because that gives them the most space. And so we get a square planar geometry. There's the table from your book. And yeah, it's too small to see on the screen. So summary of Vesper theory. We determine the geometry by looking at the number of electron groups on the central atom. And we figure that out from the Lewis structure. So you've got to start with the Lewis structure. Electron groups include lone pairs, single bonds, double bonds, triple bonds, or single electrons. Each of those counts as one group. A triple bond is not 3 groups. The geometry of the electron groups is determined by their repulsions. And the bond angles can vary because multiple bonds take up more space than single bonds, and lone pairs are even more repulsive than multiple bonds.